Hello and very good afternoon, everybody. Thank you so much for joining us. I'm Mohammad Tehrani and would like to welcome you all in the third session of the second edition of the Water Whispers Wednesdays webinars 2025. This is a sharing time which is planned to be held a couple of times during the year, sharing the hydraulics and water relevant issues. For those sessions where the speaker will attend in person, the webinar will be conducted in hybrid mode, and unfortunately this time this is not the case. Each session will feature with the dynamic presentation lasting approximately 30 to 40 minutes, followed by an interactive 20 minutes Q&A session. Before we dive into the talk, a quick reminder to please engage. Feel free to ask questions using the chat box, and we will address them in a dedicated Q&A session at the end of the presentation. Or you could turn on your mic and camera and ask your question or share your remarks directly. Today is no exception, and we have a distinguished speaker who will share his expertise on optimization of debris flows and protection structures, sharing the insights from physical model tests. Whether you are a pioneer, senior professional, or just a young beginner in this area, get ready for an engaging and informative session. Without any further ado, let me introduce our esteemed speaker for today, Dr. Dawood Farshi. He is a professor of hydraulic engineering at the Institute for Construction and Environment, IBU, at the Eastern University of Switzerland, or let's say Applied Sciences, so-called Ostad, in Rapperswil, Zurich. His work focuses on sediment transport process, debris flow dynamics, and the design and optimization of protection structures using both physical and numerical modeling. He earned his PhD from Universität der Bundeswehr Munich, Germany, specializing in hydraulic and sediment-related hazards. Prior to joining Ostad, he was involved in several applied research and engineering projects in the field of natural hazard mitigation, particularly in alpine environments. At Ostad, he leads physical model experiments in the university's hydraulic engineering laboratory and contributes to interdisciplinary research and education on flood risk, sediment management, and torrent control. He also collaborates with the national and international partners, including in Iran, where he is currently co-developing a guideline for flood hazard mapping with us at WML, or let's say Water Matters Laboratory. Dr. Farshi is passionate about bridging the gap between research and practice and promoting science-based approaches to improve resilience against natural hazards. Dawood Jan, thank you so much for accepting to be with us today, and floor is yours.
Good afternoon, ladies and gentlemen. Thank you very much, Mohammad, for your introduction.
My pleasure.
I'm very glad and happy that this opportunity has been given to me to present some insight aspects of the physical modeling, especially for debris flow protection structures. And I would like...
Sorry, excuse me, Dawood, sorry for interrupting. I guess you still need to share your screen with us.
Yes, I will do it. Yes, sorry. And let's yes. I will start with sharing my
Dawood, your microphone is muted, so please unmute your mic.
I don't know why. Yes, you can see my presentation, yes?
Yeah, we can hear you,
Yeah.
we can see your presentation.
Very well.
Yeah.
Yes, I will present you about the advantage of the physical model tests, especially for optimizing of debris flow, and why we use that, and what is the advantages of the physical model, and some special aspects what we consider here in this approach. The presentation is structured as like this agenda. I will give you a very short introduction about our hydraulic structure laboratory, about our activities here. Then I will go fastly through the debris flow introduction and what kind of the countermeasures are considered for debris flow hazards, and what is the numerical modeling and what is the physical modeling, especially in case of the debris flow. And I will show you details information about the first case study, multi-stage protective structure in Switzerland, both of the project, and the second project I will show you just information, very short information because of the time. Good. You can interrupt me anytime if you have a question, no problem. We are at the Applied Science University in Switzerland, in east of the Switzerland, under the Department of the Civil Engineering and the Environment and the Architecture. And our institute, Civil Engineering and Environment, has different competence center. They call it competence center. It was before practical centers. Now it's competence center. It changed sometimes the name. And we are 7 professors, different research assistant and the project manager and the project assistants. And we have 4 laboratories here, hydraulic structures, geotechnics testing center for building materials, and the concrete robot. And I'm responsible for the part of the hydraulic engineering, especially hydraulic structure laboratory. Our laboratory has 2 parts. One is on the campus, and the other one is close to campus outside in an industry area, where we have more possibilities to build the large models. And we have different measurement systems what we use in our investigations. You see that pictures of the one model in the outside upstream and the one in the inside in the campus area. In the campus area, we have also laboratory students, bachelor students, who through the hydraulic engineering, hydraulic lectures, they will check and do our own experiments based on the theory what they have learned at the lecture, and they do some experiments, measurements, and they give some reports. Our activities are mostly concentrated on the practical aspects. We do some physical models for different subjects: river engineering, mountain terrains, and bed load and driftwoods, also hydropower. And we do also numerical modeling, 2 and 3D modeling for different questions. We have also studies and expertise for in case of the conflicts. And we do also some software development. Means that if there is some special questions, for example, I will show you later what we also try to combine 2 physical model and numerical model together to have a hybrid modeling, and all these subjects also integrated to different projects, student projects, bachelor and the master thesis, also term projects. About the development of the software, for example, we developed a web application for sediment transport, bed load transport in natural river cross sections. which you can use also, bedload point.ch, and to give some special information where the bed cross section and the other information, you get your bed load curves based on the different discharges. This is our most activities in our laboratory. Okay, I will change to debris flow, what we want to talk about today. Yes, what is actually debris flow? This is not so easy to define a debris flow because there is no any sharp border between different water sediment movement, but I think the best defining has been did by Takahashi, and he tried to define what is the debris flow. You see that here, the overlapping between different flow systems. And if we land side from the land side and on the sleep, we can debris avalanche also, but also we have a debris inertial and the viscous debris flow. But we have also dry granular flow, which we can also be considered as a debris flow. It should be. It is important to know that there is no any exact define, but we have to define something as an engineer always. And the debris flow is a sediment and water mixture, which the sediment concentration is very high, almost area of the over 50%. But they moved also like a continuum by the gravity, and those due to the water part, they have a very high mobility. What does it mean? High mobility. You can see that here. You have very high magnitude, also very high velocities. On 220 meters per second could be the velocities of the debris flow, and the debris flow could be very different in the nature and also in flow condition, even in the same area where the debris flow can happen. I hope that these two videos could be seen. I will start first one. You see that this is Illgraben. It is a mountain torrent in Switzerland, which is very famous for debris flow. You see that this debris flow, what happened in 2000. This video, you see that the flow is not so fast. And have lots of blocks, very large blocks in front part, which is a very characteristic for debris flow, and then tail part, which is more fine sediment. If you look at the same place 1 year later, you see completely different type of the debris. If you look at it behind the next surge of the debris flow coming, and you see that this is almost a sandy, very fast flow, which is not so like the first one what we saw, and also if you we look at it later, there is another surge which comes and the same characteristic it has. It could be very different forms of debris flow and also flow characteristic, but it has also very high mobility. You see that what kind of the blocks can be moved in debris flow. Yeah, well, I don't want to show all the movie, just to show that the characteristic of debris flow. Generally, we can characterize debris flow with the multi-phase mixture, very unsteady, surging flow behavior. I show you some measurement in Japan, which shows also you see the depths, different height in the time, also frontal velocity very high and then low slowly, and time interval, and also volume of the surge. You see that different volume of the surge. It's They have high density, high velocity, and enormous transport capacity like a blocks. Therefore, they have also very high potential of the destruction if they moves towards the infrastructure or the urban area. This happened very often now because of the climate change. We have the situation, especially in mountain areas in middle of Europe and alpine area, that because of the glaciers getting back and removed, the lots of material are open to be eroded. And therefore, we have very often large events of the debris flow. 2005 was one of the severe situation and the events especially in middle of the Switzerland, close to the Bern. And you see that one urban area, small urban area, is actually a village, which is in the position area of the debris flow mountain torrent. It is located, and in 2005 there were large debris flow event, and it was 6 persons was were dead, and also lots of the buildings has been destroyed completely and also very severe. And you see that what kind of the transport capacity is available. What in case of the debris flow, 8 cubic meters, even larger. They observed also stones with the 40 cubic meters. Recently, last year, we have 3-4 debris flow events in south of Switzerland. This is an area of the Misox in the valley, which debris flow destroyed a very important highway connection, and this is actually caused lots of costs, even construction costs, not the cost what you can calculate it, what happened that highway is not in service. And also in Ticino, we had a very large event. Again in valley, you see that how much material has been transported during, and if you look at the case in Ticino, you can see the person here and what kind of the large blocks could be transported in case of the debris flow. We have a problem, and question is always that how we can save the areas, infrastructure and the urban areas against the debris flow hazards. There is a different ways to do that. You can prevent or try to stop the initiation of the debris flow with the, for example, with the forest development and the drainage system, something, but not always in the very high elevation. It's possible because after 1,800 elevation, you don't have any vegetation almost. Then it's a special planning measures. It means that you don't let the development of the urban area and the infrastructure in the area have a very high hazards or danger, and or structure measures for the areas which has already been built and are there, which is now in the very high hazards area. And this structure measures is the most used in our cases method for countermeasure. And there is some systems. The one system is that you let the debris flow through a channel which has enough capacity to let the flow debris flow, or you make diversions. It means that, like here, like a diversion works with like the walls and the dams, which divert your the debris flow, or you make a retention check dams to stop the debris flow. Good. How is the design of the debris flow actually these days? This is the very challenging system, because debris flow in nature are very complicated, also in physics. The first thing is that we have to estimate the volume of the next debris flow event. The difficulty starts already from here. Then, if you could estimate that, we have to estimate some flow conditions. What is the flow depth? What is the flow velocity? What is the peak discharge which happened? Then we try to find some topographic appropriate area for a structure. Then after that, with some empirical formulas and experience, we try, and the help of the numerical modeling, I will come back to this numerical modeling, try to define the geometry of the structure. But the most of the time for debris flow, most of the time you have to validate the system using the physical modeling. Why it is the physical modeling is still very important. I will show you the case. There is some numerical modeling systems like RAMS, which has been developed in Switzerland at the WSL at that time, that you can model you can simulate the debris flow movement in very steep area like this one. You can look at it at the left side and the right side. Which the debris flow movement and the velocity and the depth has been calculated. It is very useful, this tool, but it is not appropriate for very close area of a structure which you have a very complicated flow conditions. And it is very useful for a large area that you see that how the movement, how the debris flow deposition can happen, but close to structures, it is very difficult to use it, because it doesn't consider all of the flow dimensions. There is some efforts to simulate the debris flow 3D. Like here, we did also in a master thesis, try to model, stop it here, try to model debris flow using non-Newtonian flow using SPH system. But first, you need lots of simulation time. You see that here we simulate just 150 seconds of an event, but we needed 180 hours for that, and it was still a continuum area, one phase, not two phase, but non-Newtonian. We had a interesting results. So you see that this is the area which the debris flow moves through and this is the construction which used for the diversion of debris flow. I will come to it next in this my second case. But we see that there is also some points that we couldn't simulate. For example, we couldn't simulate the position of the debris flow on the area because it's one continuum, and because it's very steep, it moves out from the model. Therefore, it is still a state of the research. I say that debris flow simulation in 3D, even there is a very good improvement, for example, at the SLF, at the Switzerland, using not SPH, but MPM systems, but they are still for discrete elements, which means that just rock simulation, but not in combination and in the interaction with water. Therefore, the physical model is important. Physical model was important. You know it better than me that more than 100 years they are used to investigate of the special questions, and it's used for design of the hydropower plant, river morphology very often, and also countermeasures for hazards, natural hazard, and also other important point of the physical model. They are complementary to the numerical models based on because of the data that they deliver for numerical validation and also calibration. In case of the what is the advantage? This is first there is a direct observation of the real process. Some process which is not very fully understood in mathematical way, we shouldn't try to give a description. It is inside the model, and in the case of debris flow is very important because of the complexity. There is of course some limitation because of the simplification that we make scale effects. We have a laboratory constraints that we have to consider, but in the case of debris flow, we could use it because of the fruit similarity, because we have in debris flow we have very high gravity forces, inertial forces, which can be simulated in a physical model based on the fruit similarity. The scale choice is very important. Our experience showed that we have a long time experience in the physical model of debris flow at the institute here, and it showed that the typical scale model 1 to 40, 1 to 60 are give acceptable results. And how you choose which one is the appropriate one is based on your laboratory constraints. Place is one of the most important, and the height, because we are in most of the time a steep area, and if you cannot build more than 3 meters height difference, then it should be. Or one of the more important is the material management. If we talk about 100,000, for example, 40,000 cubic meters debris flow, you have to see that if it's possible to make it with 140 or 145, maybe you have so much material that it is not possible to do it in the laboratory. This is also important. One of the other limitations what we have in debris flow physical modeling is that we cannot produce a natural debris flow mixture in the laboratory. First, it is not exactly clear what kind of the mixture is that in there, because you have just some information from deposition. You cannot do measurements during debris flow event, but we have to do something. Therefore, we use a man-made mixture recipe, what we developed also in our laboratory, and then try to change the mixture based on some flow parameters that we have the same flow condition in the laboratory as the same in nature, but the mixture is not exactly the same. This is most of the happened with the two important parameters. It is the front velocity of the debris flow and the peak discharge of the debris flow. And we measured debris flow front velocity based on the distance sensors. It means that we have a sensors. I will show you next later this sensor, and we see that where is the different front, and then we have most of the time 3 sensors, and they make in the equal distance, and they make an average velocity, and it should be the same velocity as we consider could be happening in the nature. The peak discharge will be controlled with our tank, which we have also measurements, and we see that how fast the elevation of the tank change. Then we can define the peak discharge and control it. The front velocity is one of the important how we define the front velocity. Engineers who design the countermeasures try to define it based on the empirical equations. Some of them are, as I show you here, depends on the information that you have, also in which area. In Switzerland, Rickemann formula, one of them is here. He has also another estimations of the front velocity choose for that. We have done also our investigation mixture and the front velocity. We wanted to know that what kind, when and in which condition, which mixture should be used if we know the front velocity, and we define channel experiments as shown here with the half circular channel, and used our mixtures and measured in different distance the front velocity, the height of the debris flow, to see that how the front velocity change, and what is the more important parameter which affects the front velocity. You see that here some pictures of this channel. In the left side, two picture with the very smooth condition, and the right side you see the roughness that we used in our cases. The smooth showed also interesting results, that the front velocity is not so what we thought. We thought that it gets more faster, but it's not the case. Smooth, even it is almost constant. The blue ones are a mixture that has very large gravels inside it, and the red one is with fine sediment, not without large gravels. And these two pictures is related to the water content of the 70.5%, and the right pictures related to the more water. And you see that the even fine and with the gravel, they don't have a different results. It was very interesting for us because we expected other results. The results with the roughness is also more interesting, because we saw that they are even faster in the front velocity, but this is still on the investigation what happened there, and therefore I didn't show you here some picture of that. Okay, this is the actually investigation introduction to the debris flow. I don't know if there is any questions from audience to answer. If not, I will change to case studies. Okay.
Seems you could go ahead. Thank you.
Yeah. Good. Case study, what I choose is that one is a multi-stage protective structure in the area of Merecci. Merecci is in the valley in the south of Switzerland, and where the mountains are very condensed and the very high mountains are. You see that here the area which this torrent is located, and you see that some part which showed that here they estimate that if this area is activated due to the rainfall, there is a large potential of the movement up to 130,000 cubic meter of material towards to the village. And this is the ways where the debris flow can move. There is some sediment trap which is already exists in this area, but it doesn't have enough capacity. Therefore, they estimate the hazard in the hazard map, the area which is has a significant hazard, medium hazard, and the low hazard. This is this area, and this is the actually hazard maps in Switzerland are as a point of the law. It means that if you are in the red, and the red one, there is no any permission to build a new building. And if you exist in this area, you should think about that, how you protect yourself. And also the blue area has a very high restriction to build, and therefore this village, with help of the national government, they think about that to make a countermeasure to protect this area and also this important rail connection. I don't know how familiar you are with hazard maps. Maybe you can look at the hazard map of the earthquake in Iran, but based on my information, there is no any hazard map for floods and debris flow in Iran. As Mohammad said at the beginning, we had a project which was financed from Switzerland to define a technical guideline for flood hazard map in Iran. And we did it, and with case study in Poldochter, we tried to implement this hazard mapping method, and I think there will be a special meeting, or maybe in this webinar series also for that. It was very successful project. We had also very good impact also in social media for that, even from the Swiss side. Yeah. You will be informed about this project maybe in this webinar. Mohammad could say more about that later. Okay, I go back to again the hazard map. Yes, we see that the problem, we have a severe and significant and medium hazards here, and we should do something. What they did, they defined because of the topography, the only way that we can do it is that to trap and stop the debris flow in this area, and because of the volume, the first one, which was here, it doesn't have enough capacity. They have to build 2 more sediment trap or hazard debris collector and enlarge this system, and also think about this case, if it comes more sediment, what happened to that. What does it mean? It means that in Switzerland we have still now, it will be changed, but still now we have a level of the protection for different areas. For urban area, we have a level of the protection which related to the 100 years events. It should be fully protected, and if it comes more, for example 300 years and a little more larger, it shouldn't, the system shouldn't be collapsed, and also the risks should be not so large. You shouldn't have a protection 100%, but the risk should be estimated and took as small as possible. Therefore, we have also here other areas which, other structures that used for the events large. I will come back to it with the events system. Okay, what we did, we tried to make physical models in this area, which is consider all the structures. It's area in the nature 600 meters and almost 200 meters width, and with the height, which you see that this is even at 730, and it's 600, almost 100 meter different in the height. We build it in the laboratory, a very large model. It's almost 15 meters long and 3 meters width, and almost 2 meters height different. And first step was that to find out which mixture should be considered in this for this model. We define a fine and viscous part, which is we use opalite and a very fine sand for that, and it is very time consuming experiments in debris flow system, because we have to mixture the viscous and the fine part minimum 12 hours before, and then at the day of after that, at the moment of the experiment, we mix the sand and the gravel to it and make experiment test. And after the test, you should clean everything and put it in some container, and some special companies can take it and work on it, because you cannot. It's not the water circulation. Therefore it's very time consuming and very expensive experiments. What we did, we calibrated the mixture for each surge almost, and we find out that the water contained should be considered as this to the dry, or the total volume almost 1/3 of the volume. And the other thing is that very important is that you get some information based on the deposition, and also events what happened before, some information about the gravel and sand size distribution. And if you have to decide which how you can model it in the system, you cannot catch everything here. For example, we have 3 different measurements, and at the end in the discussion we decided to consider the green one for our experiments. We did 77 preliminary tests and find out that for each surge we can we have a special recipe and the mixture which we reach the target values with some errors. In peak discharge very low, and in the velocity we have some deviation with the but it was acceptable in this part. What does it mean? You can show you in this video, for example, the first one, the first mixture, which was very liquidy, and it's lot of water content. It doesn't reach the target values, but the second one, which is under one, was the same. And you see that here these 3 measurement area, which we are almost, you cannot see it, but almost equal distance, and based on these values we calculate the water debris flow front velocity. Okay, even almost during this preliminary tests, we find out that there is some shortage in the design of the countermeasures, and this is the first which needs some optimization. This was the first optimization based on the preliminary test. We find out that the height of the dams in the first collector was very low, and it needs to be heightened in left and right side. That was the first optimization, which it should be almost 3 to 5 meters heightening of the dams of the first collector. Then we try to check the functionality of the overflow section. What does it mean, overflow section? I will show you this area. You see that here, the different collectors, and two of the collectors, they have an overflow area, and we wanted to check them if they works well. And debris flow, as you see that they have a different, very unsteady nature, and also it means that they can happen very shortly, short time distances. And it was the question, what happened if we could not empty the collectors, and the next large surge will come, and what happened? And the question is that because of the time, therefore we consider the wet material, and also because of the management. Maybe they forget it. It happens sometimes. They forget to empty the collector, and it could be happen that it is there and they are dried. The water is gone, and what happened if it's dried? Yeah, this is, you see that, for example, this situation which the collector are filled with the fresh material, wet material, and we checked it, what happened. Yes, what does it mean? What happened? I show you here case. It is I don't want to show all the videos of this. Almost more than 1 year we checked all the scenarios, but this is the case which is filled with the sediment, and a large surge with the 40,000 cubic meters are released. And we see that here what happened. The first one is overflow, then the second one, and also the overflow section, which is considered for the material which is more than the design value, is also overflow here. We measured every very important points, and you see that the results here, how is the height change in different sensors. Different sensors what we put. You see that all sensors what we put in the model. Then based on this, it comes to the second optimization, that we see that the overflow section on the both sides needs a special overflow in the first. That means that first we heighten it, and then we see that no, it doesn't work well, because this overflow doesn't work well. We make it in 2 stages. For the large surges, it comes to overflow this area. For the small one, this is this area. And then also uniform lowering of the other overflow section. What does it mean? Overflow this and this part here. Overflow 2B and 2A, 2B. This is this one. Overflow to this one and this one. We have to lowering that with the hope that it works well. Then in collector 2, you see that there is lowering of the overflow, this area, but we did it, and therefore we have to make it small, this pier here, and the adjustment of the dam slope collector 3 was also a part of the modification. Then, sorry. also in the collector tree, we have to change the overflow and also widening this area to be able to bring more material out of the collector in case of we have a larger values. You see here the sequences of the multiple. I don't want to show all them because it was not a place to show it. We have a sequence 4 here, 4, 1, 4, 2, and the sequence 5 system. We have different surges, combination of the surges for different return period. For example, the first one is only until event with the 30 years return period. Then the sequence 4.2 is until 100 return period, and sequence 5 is with until 300. I will show you this sequence 5 after some modification. This is which shows us 130,000. This is the largest value. It is the last surge which is released from the tank, and show that how the collectors work and also how this overflow also works. Shows that this area which is considered for the case with the larger events than our protection level, that it helps to stop the debris flow before it hits the area which is makes more risks. Then it comes to the third optimization. You see that it's very iterative system, that we have to rise more the dams behind this overflow to stop the overflowing the dams, because if the dams are overtopping, then it's very expensive to construct it. Then we find out that the overflow in the collector of 2, it doesn't work well. It means that if you look at this system, you see, sorry, I go back. We have lowering, and at the end we find out that the dynamic of the flow, which comes from the first collector to the second collector, is so high that this overflow of the left side doesn't help us to bring the material outside of the. Everything goes to the collector tree. Therefore, we decided to close it, and to make it more effective to flow over the trapped collector 2 to 3, we decided to change the topography in the collector 2, and it helps also to stability of the dams. Then next one, we see that we have to change the beam barrier, which is responsible to close the collector, to change it to the smaller distance to make it more effective to stop the debris flow through the channel outside of the collector tree. And at the end, we made also some, based on the results, we make some suggestion that the first, that this dam, which was considered to stop the overflowing of the debris because of this curve, they thought that debris flow over top the river bank and comes out, and we see that none of the surge could overtop this, and it means it doesn't need that. This one, we found to arrange the this dams here. We can make it appropriate to the topography, and also closing this one and make it cheaper to build it. And also because of closing of this overflow, we don't need this diverting dams for the overflowing. We have to change it to this part. And from that point of the view, the conclusion was that these physical models showed that structure which seems actually at the beginning not so complicated because it's a sediment trap or a collector only. It shows that even in this case we have lots of optimization that makes the structure functional to the level of the protection. And the comparison of the costs, what we use in our models to the building cost, it shows that it's very useful tools to invest it because you achieve the through the optimization and the validation the functionality which is more secure than only based on some empirical equations. Also, we have, of course, from physical models because of the controlling system, measurement system, we have good data that we can use for our numerical method. Then I will go to the next debris flow case just to show you another example. This is also a hazard map to the debris flow, and also a village is in danger area, large of the structures, and they wanted to eliminate these danger areas from the hazard maps based on a diversion system, and they found out that this is the best area. We built a diversion wall and doesn't let the debris flow go through the torrent to the village. They will divert it to this area, which is actually agriculture area. We made also a model, investigated in the model 140. It was because of the material, what the surge volume. We could also make it smaller, but we cannot, we couldn't do it because of the volume of the material, and tested if the system what they considered here, these two diversion walls, if it works well or not, and also if this construction which is considered in the river is only for the debris flow, water should go through, it's work well or not. I don't go to the details because of the time, but I want to show you this is the case. It is 20,000 cubic meters in the first surge. It could comes and show that how it works, and after 2-3 optimization, we could find the best form of this structure, and also the appropriate height of the walls could be considered. Also, we could define how much material could be diverted, and which part of this is deposited in the river or not. You see this part, maybe just a short reference to the measurement system. You see that it is very wavy data in comparison to the other videos which I showed you in, because we use in this case use a laser distance meter sensors. The other one was the ultrasonic, and the lasers are very sensitive to the very small movement. It means that sometimes some small stone jumped from the debris and it catch it, and it needs, if you use laser distance sensor, it needs some post-processing to eliminate such a noisy signals, which is not actually a real case, because the water debris flow elevation doesn't change so fast. Okay, then I coming to the closing my presentation, just with some information that the next presentation will be held at the 15th of October, and we hope that you will save that And thank you for your attention and time for my presentation.
Thank you so much, Davud. Thank you so much for enlightening presentation. I by myself really enjoyed, and actually I enjoyed the recipe. You called the recipe for the
Yes.
the flow. It was the first time that I have heard it, but I think that's a good term.
Yes.
Yeah, actually, it's time for Q&A. I'm going to our audiences. I have by myself some questions, but we have already a question
Yes, that's,
received
I saw that.
from
I saw it,
Matthew.
yes.
Exactly.
Yes.
Since it's just, I mean, since the session is in English, I will just try to translate it in English, and then you will answer it. It was the greetings about some local, let's say, how can I say, uh, ah, uh, what do what do we call? I
Yes.
just forgotten.
I
Yeah,
think the question is about the erosion systems,
exactly the local
because
erosion
yes,
in the vicinity of the hydraulic structures. Exactly
yes,
in physical
that's
modeling,
yes,
how we
that's
could present them, or let's say transfer them to the real scale.
yes.
Yeah.
In case of the structures, if we have structures like also in Merici or the other one what I show, close to the structure, they will protect it close to the structure with the boulders, with the fixed boulders set in the concrete, that there's no any erosion happened. But the important point, what Mr. Destani said, that is that in our model, as you see that also in pictures, you see that also in this model, there is some boulders set in the river, but they are fixed. We don't consider the erosion of the river, the torrent, and also banks in the model, because it makes it very complicated for the reproducibility of the results. I should add to the modeling of the physical modeling of the debris flow. We do every experiment or every test 3 times, because debris flow are very sensitive to the temperature, to the water content, and something, and also to the time what we make the mixture. Therefore, we do it always 3 times with each search to get some average results. And if we consider the erosion of the model, it will be very complicated to control it. And the debris, and another point of the debris flow model is a practical way. The most of the debris flow model is very large, as you see that, and you should walk on it. And to control it, to test it, and to put the measurements, and if it's movable, it's not possible to walk on the model, and therefore it's considered the results. But if there is some special case that we did one time, that we close to some structure, we put the material erodible, and to see that what happened. Most of time in the debris flow, it is some simplification. I said that I wrote it here also, fixed bed, no erosion. This is some simplification that we do in our model, physical model.
Good. Thank you so much for addressing this question. Well, we do not receive any question yet. Please feel free to share your question or remark with us. I have seen some, familiar and unfamiliar names, and I have seen that we had some others that I'm not sure if they are okay. Perhaps there was a problem with that, so they are joining us again. Yeah. Meanwhile, I could ask that. Well, I have visited your laboratory, and I have
Yes.
got some let's say results from the numerical one. And actually, we have shared also, or the key home messages that you have shared with us. Well, actually, this is the main question that normally I receive during my physical modeling classes. Nowadays, we have the most, let's say, powerful or strong, let's say, results from the numerical model ever we have had. But we are still sticking to the laboratory experiment or physical modeling. Is there any justification for that? Is there any, let's say, problem with changing from physical modeling to
Yes.
numerical one?
Yes, in some cases, we change to the numerical modeling, especially if you have, for example, say that if you have just fluid flow, for example, just water flow, then we can also investigate only numerical model. Even there, the problem is that even there we have some parameters that we have to set, and if we don't have any validation or calibration values, it is very difficult to say that how large are the results predictable, because it could be 20%, 30% if there you have a very high velocity. But especially in debris flow, I would say that because the measurements are so complicated, because you cannot see the flow conditions, you cannot measure inside the debris flow because it's very destructive mixture. Therefore, it is still just some parameters that you can observe or measure from outside, just height or something like that. Therefore, it's not so clear how we can model it physically. There is what can I say? Yep. Some try to model it with multi-physics, but the problem is that more complicated model needs also more parameters which should be adjusted, and the question is that how we can adjust it. Do we have information about the velocity profile inside of the debris flow? How is the force between the fluid and the viscous fluid, and also boulders and small sediments? This is the point that it is not clear, and therefore, for example, we use SPH. They use MPM at the SLF. They can model it lots of landslides, but when it comes to the water, it is very difficult. It will be complicated. I say that still in the debris flow, this is still some important and unavoidable feature that we have to use it. It is the physical modeling.
Thank you so much. Since still there is no other comments or question, I would like just to extend my question that therefore, is it possible if we could extend your results from the mixture, the topography, and etc., what you have done to the condition like what we have in west of Iran in Zagros area when we have the debris flow? Is it possible, or I mean,
yes,
do you see
I
any
think
bridges or any room for that?
yes. Actually, it's a universal recipe. I say the recipe always, mixture recipe. It's universal recipe, and it's possible. The important is that to have some estimation of the target values. See that how large is the target value, but it is always usable in different areas, because I said that we don't simulate the same mixture. We just simulate a mixture which reflects the flow conditions in the nature.
Perfect. Thank you so much. Okay, I think everybody okay. There is Karim. Okay, go ahead, Karim. I think you have the permission, no? Uh, yeah, Karim, go ahead, please.
I think you should click on this point, change it to the audience, change it. Otherwise, you have only
Yeah, that's
headset.
true.
Not
I
you,
think.
Mr. Alizad should do it by himself.
Okay. Karim, could you please turn on your mic? I'm just checking if. Yeah.
Can you hear me now?
Yes.
Yeah, we do.
Okay. Okay.
Good.
Thanks, Dawood, for your great presentation. Actually, my question maybe is out of the context, maybe, I don't know. But I'm looking for some innovative suggestions. As you know, what I can say, these small channels in Tehran, we call it Jube, and we have a lot of problem, you know, with the trash there. So maybe we need to think about an innovative way to these kinds of, we call it debris flow. But I just want to know if you have any kind of suggestions, if we can start thinking about some innovative ways for such things, because it makes a lot of problem for that, for our um, um, I can say stormwater management system. So that's my question. I don't know if how related it is, but that's my.
I get it. Is it the trash? Is the floating trash?
Yes, sometimes it flows, sometimes yeah, mostly it flows.
It's if it's floating, it means that it's under the over the water. Movement of the trash is over the water, which most of the time you have this problem, especially with the plastic trash. Yes, there is some image. Okay, we don't work it on it here, but I know that the University of Technical University of the Munich, in their laboratory, they work it on such a method to divide the trash, special plastic trash, from the water before it comes to the problems, especially, for example, to the culverts, which is you have some trash racks, and it is going to close it and stop the water flow. They do some such works, how they can divide the trash, because I will refer that you can look at their homepage, and also if I can find something, I can send you. I was there and I saw the experiments, but I don't know exactly the details here. There is some innovation methods that they want to use it, especially to get the trash in flowing water, with innovative system, automatically out of the water before it comes to problems.
Awesome.
I hope that
Thank
I
you.
could answer
I
your
appreciate
question.
if you can share it with us.
Yes,
Thanks.
if I see something, I will send to Mohammad to give you.
Awesome.
Sure.
Thanks.
Thank you so much. Great. Okay, so I think there is no other comments or question from our audience's side. So just reminding that we would like to take a group photo at the end, since Dawood also is going to leave us to join his class in, I think, a few minutes, I guess. So please turn on your cameras, everybody, those who would like. We will make a group photo, and then we will conclude the session. Meanwhile, I will, let's say, invite you to book your calendar for next, let's say, presentation, which will be held on the 15th of October, where Stefano will share his insights with us. And, well, last but not the least, thank you so much, Dawood, for accepting our invitation and your time and sharing the very interesting insight with us. Actually, I could also, meanwhile that everybody is going to turn on their camera, I remember that we had a student here in KNTU, Mohammad Musa Kazem. He was working on the results of the debris flow that we have had. He somehow, let's say, took some steps, and then he finished and he went to Sweden, I believe. Yeah. Then, if there will be any interesting or anybody who is interested in these topics, we could set something joint with Dawood as well. So approach
My
us.
pleasure. It was my pleasure to be able to present some points of the physical modelings of the debris flow.
Yeah.
What we did here.
Thank you so much. You are always kind to us. Perfect. So I think we could go further for a group photo. Oh, okay. They are a bit joining us. Yeah, Mr. Mirkatuli and Mrs. Bakhshande, please take a group photo snapshot. I have done as well. So hope that our screenshots went well. Thank you so much, Dawoodjan. Thank you so much again, and wish you a nice afternoon, let's say, early afternoon. Yeah, and the others, the nice evening. Thank you so much, everybody, and have a nice day. Bye-bye.
Thank you very much. Have a nice evening.
Thank you.
Bye-bye.
Thank you. Ciao, bye-bye.